Okay, we are going to work on the volcanic rocks now. So the first thing we'd like to emphasize is certainly that here it's more of a game of looking at the texture really that is apparent when we examine volcanic rocks. So we are going to deal firstly with the intermediate or hypabyssal, more correctly, hypabyssal rocks. So rocks that didn't form really at surface while the lava was solidifying or as a pyroclastic product. So we have a few examples really here. We will start with maybe this example here. So definitely in this case I can see large phenocrysts, okay? These are relatively well crystallized. I can also recognize within these crystals evidence of symmetry. So I can see that these are sort of stubby prisms and they are sort of represented by a number of cleavages. And in this particular case, I can see at least one cleavage in this direction, as well as another sort of set of cleavages. And on this other surface, I can still see some of the same cleavage for sure, as well as a parallel cleavage. So I can see at least 3 cleavages in these particular crystals, which is helping me with the characterization. It's also quite hard, but not as hard as quartz. So I would argue that these are my plagioclase. So plagioclase is most likely based also on the color of this volcanic rock because of this microcrystalline matrix that appears to be either andesitic or basaltic in composition. So I can see very small crystals here, which I don't think you will be able to see on the camera, but if I use a magnification, which we will do, you will see small, tiny, elongated crystals that represent mostly pyroxene. So plagioclase, pyroxene, a rock that certainly is in the same field as gabbros that we were seeing before, but it did actually crystallize for some times at depth, but then more closely to surface, which explains the big difference in grain size observed. And so this really could be termed more correctly as either an andesitic or a basaltic porphyry. Okay, so I'm sort of spilling out names now, but yeah, if we focus really on some of the descriptive features here, I would definitely describe really well the phenocrysts and then discuss the difference in grain size, and this would give me, based on the mineralogy and the structure of the rock, a good indication that we are dealing with a porphyric rock. Here you can see also some overgrowths on the K feldspar, which are quite characteristics. Usually when you have cooling, you tend to have that you change the composition progressively while you crystallize the feldspar, and so you have a change also, a slight change in color here, which although could be also due to alteration. So you have to look carefully at all the crystal. In fact, here the color doesn't really change that much, but sometimes like in tourmaline you can see clearly a variation in color, and that's a characteristic of variation in temperature during crystallization, which influences the composition of either the feldspar or I was talking about tourmaline, so a cyclosilicate that forms with those characteristic transitions in color. Another good example would be the olivine. Also, olivine can transition from iron-rich to magnesium-rich variety depending on the temperature or during rapid cooling. So you will find what are called zoned crystals because they have internal zoning with a variable composition. The same is true for garnet. Also, metamorphic minerals can have this type of characteristic growth. And so this is an example. Here you see a variation with essentially multiple overgrowths of crystals of feldspar. Here this could be also some pyroxene that was deposited on the surface of some of these fractures along a crystal of plagioclase. Here I see better these dark minerals, so mafic minerals. This appears to be quite soft, so there could be also some biotite in this particular specimen, which is quite rare, but this could be also the product of alteration. So it's difficult to tell. Definitely these are quite soft. So there could be also some biotite in this specimen. I don't see any olivine. Sometimes you might find also olivine in basalts. Okay, and this other rock is similar in terms of texture. This one is really nice because it gives you the feeling of a real porphyric texture. So porphyries have this characteristic sort of texture with very coarse phenocrysts. You can see the zoning here on some of these K feldspar. You can see that it's quite pinkish in some cases, and especially the inside or the central part of this basal is much more pinkish than the periphery, which sort of suggests that you have, a transition from more potassic-rich compositions in the center, and then you move away and start to form more plagioclase-rich composition. So again, we can have overgrowths and transitions depending on the temperature conditions of crystallization, but dominantly I would interpret this rock macroscopically speaking as a rock dominated by K feldspar, and I can see also that it does have a fine-grained matrix which still has also dark phenocrysts. So for example, this here is pseudo-hexagonal, so difficult to see, but I have a pseudo-hexagonal basal there, another here, and so I could interpret these basals as a good indication that they have mostly biotite in this specimen, because I don't see any elongated section. When you start to have, and this is because of the way you break biotite. So biotite quite often will break along the single cleavage, and so it tends to form fragments that are essentially small layers, or thin, more correctly, thin layers. And so that's why you lose completely those squared sections that are more typical of pyroxene and amphibole. So that's an important observation to make. Rock dominated by biotite, a lot of K feldspar, so it gives you an indication that this porphyry is much more silicic, so it's the opposite really end member if compared with this plagioclase-rich porphyry. So this porphyric rock, it could be, either a trachyte or a rhyolite porphyry, but I don't see a lot of quartz, so I would call this a trachyte just based on the composition. that I can recognize in this rock based on the phenocrysts. This is a slightly different beast, and I would put it in together with things like these specimens, so we'll leave this for later. And for example, this one here, this one, and this one. So what I can observe is a change, significant change in mineralogy, and I can see that this is magnetic. So what is this thing? Okay, so let's look at it carefully. I definitely see mostly a very fine grain microcrystalline matrix and some inclusions, and these are quite irregular and have a variable composition. So they look either crystals or clasts or a combination of them. So for example, here I have pinkish fragments which also would indicate that this rock contains K-feldspar, and also I have strange things like this spherule here. If you saw, I've noted that it was magnetic, so this is composed likely of sulfides such as pyrrhotite. And so, it does have the appearance of a rock that is volcanic partly, but has a quite unusual composition, because this could be misled with the basalt. But at the same time it does contain K-feldspar, which is quite unusual, and also have these spherical inclusions of sulfides, which are also quite unusual as well. So this is telling me that this rock is quite atypical from normal rocks, and in fact it's one of the Onaping breccias specimen. So it could be interpreted as a volcanic breccia, but in reality it's the result of an impact, and as a consequence of that it does have all sort of aberration with respect to its composition, which is related to the fact that an asteroid could be highly enriched in metals. So nickel, copper, and other metals are part of large impacts, and this will explain, for example, some of the spherulites that you identify in this specimen that have a sulfide-rich composition because of the separation from these melts of high elevated contents of nickel and PGE sulfides. So nickel, copper, PGE sulfides will be really the exception. Fragments of K-feldspar, questioning, what are they doing in a rock of this composition. And so most of this rock it's really the result of an impact. So you can have many different things that really compose this, and it would be classified as an impact breccia, essentially. So that's why I placed this specimen close to this other, because these are other volcanic breccias. So these are rather produced by a volcanic event, which tends to be explosive in some cases. We saw examples of explosive volcanism, and we have also a lot of hydrothermal activity that is commonly associated with the volcanism. And so it's logical to expect that there will be fragmentation taking place and the infill with hydrothermal fluids associated with this brecciation that occurs in the rock. So if we have a basaltic composition, so assuming this is a basalt, we are fragmenting the basalt, and we have an infill of quartz. So in this case, this is amethyst because it's very strong. So I don't think it's a carbonate or fluorite. It's really too strong. It's even hard with the still file to actually scratch it. And then I have some sulfides as well present. This is submetallic honey-colored sulfides. So most likely these are crystals of sphalerite. So you can see here this characteristic honey color, which is an indication of the fact that this sphalerite is present. So a volcanic breccia also could be termed as jigsaw breccia because of these fragments essentially being ruptures of larger fragments which are located in the same position where they were originally. So there hasn't been a lot of movement in this case, and so some of the deformation has been localized, and this breccia has been cemented with fragments that are pretty much in the same position. This is also suggested by the composition of this clast. So these are not phenocrysts, they are clasts, so fragments of pre-existing basalt, and these also are fragments that didn't move much because they have pretty much the same composition. So that's your an example of volcanic breccia. This is another example of that with more concretionary textures. So we have, in this particular case, deformation of precipitation and solution processes, which led to this coliform texture in which what I believe it's quartz is actually infilling these fractures. I still have some sphalerite, and you can recognize the adamantine luster as well as the variety of colors in these crystals, which tend to be yellowish in places and more reddish in others, which is another indication that this is a sulfide, in particular a zinc sulfide. And so some of these textures are quite often found in mineral deposits such as Mississippi Valley type deposits, which are sedimentary related deposits, but in some instances you can find them also in volcanic massive sulfide deposits, so associated with volcanic rocks, and because of that you can interpret this as a volcanic breccia as well. This last specimen, it's not really a breccia. We have that some of these clasts that we were discussing earlier are quite irregular in shape, but they form sort of layers that are more indicative of a depositional process. So something has deposited, and in particular in this case, based on what we see, we have a lot of silica, we have sort of very tiny microcrystalline fragments that could be cinerites, and then we have these larger clasts that have either siliceous or they're feldspar rich in terms of composition. So I would argue that this is likely a tufaceous rock or actually an ignimbrite, so a deposit that could be termed as a pyroclastic flow. So pyroclastic flow deposits will form these characteristic stacked assemblages with sort of these trends which are related to the compaction of the pyroclastic deposit. So that's your quite commonly an ignimbrite or a pyroclastic rock. Okay, so we have addressed the breccias and pyroclastic deposits. We could talk about this because this is also a pyroclastic deposit, but it does have a different composition and also special structure. So you could call a tuff also this, and in particular a welded tuff because of the flames. So le fiamme in Italian are actually fragments of glass that gets accumulated in a pyroclastic flow and can form essentially layers of highly silicic composition. So you can see here it's very reflective like quartz, so very glassy, and very dark like obsidian. So you could classify this as an obsidian or a volcanic glass. And what happens is that we have essentially these glass shards that are deposited and they are within a sinerite. And so if the thickness gets very, very big in a short amount of time, you maintain the temperature, you tend to melt the glass and form these glass flames, which tend to have this characteristic thinning laterally. So you can see here, for example, this lens of glass that is thinning out. So when it thins out like this, it's an indication of compaction. So the compaction acted in this direction. So you have essentially a process that squeezes these, and since these are very hot, the glass will melt, and so you have melting or welding, and this is why you call it a welded tuff. So it goes hand in hand with these other very similar processes of formation, with the deposition of cinerites and the deformation or arrangement of clasts according to a stratification, basically. Okay. Other examples of volcanic rocks, I think we could move into these ones that are highly vesicular, and we will have to make a small experiment that shows the difference between essentially pyroclastic products that are formed by highly silicic magmas that are called pumices, as well as scoria, as well as these other lavas that are more basaltic in composition, and they all have this feature in common, that is the abundance of vesicles. So whenever you enter in or you are in the position of you classifying an igneous rock that is highly vesicular, a recommendation is certainly to look at the weight or the density of the rocks. So if they're really heavy, they are most likely rocks that are either a basalt or a scoria, which have the same composition actually. So also the scoria is basaltic, but it's just a process of formation that changes. So usually these are a bit lighter. This will be more competent and harder, and that's because although they have similar composition, the proportion of gases in a basalt that is a vesicular basalt will be lower if compared to a rock like this, which is a scoria. So you cannot really eject this as a fragment. It's much harder, and quite often it's more lava that essentially has this process of degassing taking place, and so a basalt can liberate gases in a subaerial process, and it will form a vesicular basalt. So you have two examples here with a different degree of alteration. Of course, if you start to oxidize the iron and magnesium minerals that are contained in here, which are the ferromagnesium silicates, so mostly the pyroxene, we liberate the iron and oxidize it, and you will form through weathering rocks that are more reddish to yellowish in color. so depending on the type of oxides or hydroxides that you form. So that's quite interesting. It's interesting also to find that this bubble or vesicles have an elongation in them. So when they are elongated like this, it's indicative of compaction, and so it's more easy to interpret it as a thicker pile of lava that has sort of at the phase of degassing, and then some of these bubbles have been compacted and led to this characteristic texture. So you can see here that the bubbles are ellipsoidal in shape, so they have essentially a major semi-axis, which is an indication of the stretching direction. Okay, we can look at this other example, which is very similar. So if you have lava like this, this is more of a different composition. The reddish color is telling me that either it was heavily weathered, or it could be actually a rhyolitic composition. We would have to sort of cut a thin section and look carefully at it. But another feature that is remarkable here is the fact that these are forming amygdals. So the bubbles have been stretched, so I have a flow structure which is indicative of a lava, and at the same time I have a situation in which the cement is actually infilling the amygdals. We would have to establish the composition of the cement. As I stated earlier, it could be either carbonates, clays, like zeolites, or quartz. So silica can infill these. So in this case, we could test it with the acid. So if we pick up the acid, which I think it's in here, and we test it very rapidly, we should be able to test if it's and it doesn't look like carbonate because it doesn't fit very much. So in this case, I think I would be more inclined to think that that's quartz, because also the hardness. So clays are very soft, so if you have to recognize the difference, but it could be, I think I can scratch this quite easily, so there could be clays actually. These are likely clays. So it could be combinations of epidote and clays, really in these particular vesicles. So easy to scratch, therefore not quartz. Here I have another example of vesicles. These are much more greenish in color. So in this particular case, I would definitely interpret the vesicles as representing epidote in composition. So they likely have epidote, and I can definitely see much more clays in here as well. See, I can scratch it quite easily. So a combination of clays and zeolites, and also this pistachio green, when it forms infills in the vesicles, is more likely this pistacite or epidote variety, really, of amygdals, or epidote-rich variety for these amygdals. So still a volcanic rock. Here in this case, the vesicles are pseudospherical, so not a lot of flattening taking place for those specific examples. Let's see if this one has carbonate, just to give you the full perspective, and you can see that clearly it's fizzing. So we have identified the example of vesicles that are infilled with carbonate, so calcite in this particular case. So for the description, of these rocks, it's important really to describe the microgranular matrix and think of this rock as likely either an andesite or a basalt, and then discuss the vesicles that form and their composition, and that would be enough really, and the shape of the vesicles as well. We have another example here that is has very large vesicles, and I can even have here probably some K-feldspar actually filling some of these, or could be carbonate as well. No, it's carbonate because it's physis. So let's see this one, see how it fizzes vividly. So many times the basalt, it's unlikely to have K-feldspar. It's most likely, you know, the pinkish in this case, it's a carbonate, and I can definitely see also some of the cleavage, although this could be also the result of accretion of this particular vein of carbonate. But yeah, remember the carbonate has cleavage as well, so you might be able to recognize some of the cleavage in the crystals, and I believe I can see some of the rhomboedral faces also in this particular case here. So if I twist it, probably you'll be able to see. But yeah, most of these cavities have been infilled by carbonate as well, so you do not exclusively form well-rounded vesicles. Sometimes they look more convoluted, and they may have the appearance of a vein rather than a vesicle. So in fact, some of these could be actually fractures that have been infilled by a carbonatic cement. But certainly an interesting example, which is the same here. So we have other sort of isolated vesicles still infilled by carbonate. Let's do another test here and see if I'm right. And it fizzes vividly, so definitely this is calcite. Okay, so we've done, I have to be careful not to forget some specimens, so let's leave these here, and pretty much we have completed this. Of course, these are the easiest. This is your basalt, and I can definitely see a microcrystalline or microgranular texture, no real well-developed crystals. I would need really a big end lens to be able to recognize them, or cut a thin section. But yeah, when you have a rock competent like this, really dark, and you can see that it has sort of very tiny crystals in it, so it shines quite a bit. So it's still a crystalline rock, but you know, microcrystalline, so maybe most likely a basalt in this particular case. And the same is true for this specimen in here. I don't really see a lot of crystals in here. I only see tiny crystals in this case and here, and this could be just some plagioclase, so some lath of plagioclase, but for the majority the matrix is represented by very tiny microcrystalline structure, and so that's another basalt or an andesite, depending on the model classification. So you will have to cut a thin section and evaluate that aspect. Okay, we are left with returning to the vesicles. I was forgetting about these specimens, which are the Pumices and Scoria. So if you remember, we discussed Scoria as coming off cinder cones, and those are, you know, found on Hawaiian volcanoes, for example. So if you take a scoria, which is usually dark reddish in color, and you sink it in water, in theory it should essentially mostly subside, and basically it doesn't float. In fact, I don't see it really floating that much. But if you take a piece of pumice, well, in theory the pumice should stay afloat, and that's an example that this time works reasonably well. So I can definitely see that it's floating on the surface. So sometimes it floats a little bit under, but yeah, don't be discouraged. The fact that a piece of rock can float on water is quite amazing. And that's related to the cavities, you know, the fact that you have large volume of this rock that is filled by air, basically. And so air is lighter than water, has a lower density, and this allows the rock to float. So that's the experience, really. So if we lift it, you will see clearly that this, apologies, this is your scoria, and that's your pumice. So they have similar structure, different color. So because that's a basaltic composition, that's mostly, you know, very high silica content in this one. So mostly quartz. So it's a sinerite basically. So very acid magmas produce the pumices. And yeah, a famous Italian island is the island of Lipari, which is a volcanic island and has entire beaches that are filled with these pumices, which are also very good for scratching your skin. So they are used really as an abrasive material. So pumice can be used as an abrasive material as well. Okay, so that's one good experiment. We have to look also at the obsidians. So these are obsidians. So when you get a specimen like this that is very reflective, so it doesn't really look as an opaque rock. It shines quite a bit, and also it's very sharp, so you have to be careful also when you handle obsidian. In fact, it was used in ancient times, so we think at the origin of man, the obsidians were used as a tool, so you can break it and form these sharp edges, so you could you know, use it as a knife for butchering of wildlife that you have hunted. So hunters in the prehistoria were using these quite a bit as a tool, because they can cut easily anything. And that's related to the hardness of this. So this is volcanic glass, obsidian, and so the hardness is close to 7, really. There are some interesting things in obsidians. Sometimes you will find similar cavities, and they will be filled with clays. So remember that you can describe the mineralogy of the cavities. You could test for carbonates, for example, and see whether you have any response. And it looks like in this case, this is a classical product of alteration of the obsidian. So if you alter glass, quite often you end up with clays as a result of that alteration. And so that's not uncommon, really, to find clays associated with obsidians. Another important feature, so remember they will be very dark, so describe it as black glass basically. And also the other characteristic is that if you look carefully, they're very curved, they have surface that are very irregular. So there is no cleavage in this rock because this is amorph silica. And so they form this crinkly, very curved, or conchoidal fracturing more correctly. So you have conchoidal fractures forming, which are another diagnostic feature for volcanic glass. In this other example here, we have also that the quartz, probably this glass was quenched at relatively high pressures because the high temperature, high pressure variety of quartz sometimes form these dendritic crystals. So this will be termed as cristobalite. and so you have these flowery structures forming inside the obsidian, but the composition is the same. But in this case, these are crystals of cristobalite that grew inside the obsidian. And so this is a particular phase because quartz has different polymorphs, and so an high pressure temperature polymorphs would be cristobalite in this particular case. You have other, so for example, 3D mites will be also another one, so beta and alpha quartz commonly called. So varieties of quartz can form with slightly different structures depending on pressure temperature conditions, and those are commonly called different polymorphs, so pretty much similar to what happens to graphite and diamond as we discussed in the first lecture. I think I'm left with this other specimen, which is characteristically reddish in color. This could be either product of weathering or really evidence that you have quite a bit of K-feldspar in this rock. I would carefully look at the rock with a magnifier, and we will do that and try to identify some of the mineralogy, and I can definitely say that there seems to be some K-feldspar in this rock. Do I see any other thing in here? I can see dark fragments in here, and they are quite reflective. So that's another thing that is very similar to what I see here. See how this is reflective. So it's glassy. The luster is vitreous for these small fragments. So small dark fragments with glassy appearance indicate that there is free glass in this rock. So K-feldspar, some glass, that's a good indication of a potential rhyolite. So this could be a rhyolite. The same could be true for this rock, but you can see here we have much more mafic minerals present. So that's also a thing you have to be careful with if you start to see a lot of mafics, which are illustrated by the elongated sections. So if you remember, I mentioned the existence of amphibole and pyroxene. So existence of amphibole, can tell you that you are dealing either with an intermediate rock like a latite or a dacite in those particular cases. So this rock could be classified as a dacite or latite, or even a andesite in some cases might have this peculiar mineral assemblage. So again, we need magnification. We need to identify some of the minerals if we can, and also evaluate if there is free glass in this rock to make sure that we are classifying correctly the rock. If it's a latite, it will have very little or no quartz, and so in those cases we tend to have no evidence of free glass in the rock, basically. But yeah, if you classify a rock based on the abundance of quartz, rhyolite and dacite pretty much will have the same amount of quartz, but you have a transition in terms of the amount of mafics in that specific assemblage. Okay, so I think I have addressed most of the specimens. I am left only with the ultramafic examples, and I left them here. So again, if we consider these very characteristic elongated or bladed crystals of olivine, this is quite distinctive of very high temperature Archean basalts, which are the comadites. So these are very unique textures. You can see here another specimen with these radiated crystals of olivine that have been replaced by likely chlorite, so the alteration essentially of the ultramafic rock, or recrystallization potentially during metamorphism of these rocks, will sort of replace the original composition of the olivine, and this is why it gets so dark. But yeah, that's an indication that you had a relatively slow cooling of this rock. So this would put the rock very close to an hypabyssal rock, although this is quite a shallow rock type in terms of its formation, because it forms in large plateaus essentially. So these are lavas that were flowing, and they formed a crust that preserved the conditions of temperature. So for the underlying flows of these lavas that were on the order of 600 degrees in temperature, we added that the crystal had the time to actually grow and crystallize really well. That's why you get these characteristic crowded textures, which are related to the fact that you have also fractionation taking place with these highly magnesium-rich lavas. So that's your komatites, and this is the ultramafic example of a basalt that contains peridotite xenolites. So this is your peridotites. I would have probably better described these as plutonic rocks, but yeah, this is also vesicular, so you could classify this rock as a vesicular basalt that has also some unusual inclusions or xenolites that have a variable composition, because if you look carefully at these, you will see more brownish colored or goldish colored parts in this rock, and then you have more deep green portions in here, and then you have more olive green portions or crystals. So the light green to olive green is the olivine, which is highly abundant. And then the dark green will be diopside, so pyroxene. And then you have also other olivine that is more yellowish in color because of the alteration. So some of the olivine usually alter into edingsites. So in some of the peridotites you can find edingite, which usually is more brownish in color because of the alteration. So I believe that could be an explanation for the appearance. Then you have more darker minerals in here, and this will be likely the pyroxene as well. So you might have augites forming in iron-rich pyroxene in the peridotite. So a variety really of pyroxene with different composition, more calcic versus more iron-rich varieties. So bear that in mind. We have different mineralogy inside the peridotite, and you need to be able to sort of figure out what the different minerals are depending on color, luster, and also hardness. So you could test for hardness and see this is really hard, so it should be around 6. So I believe that's a pure pyroxene as well. Okay, that's the end, I think, for this session today. We have completed this survey of igneous rock. Of course, if there are questions, I will be always available via email, and we will also discuss during lecture and labs these characteristics of the rock. So hopefully this has been enough as a virtual experience for you to get the impression of the different types of igneous rocks that you need to be familiar with. In the next lab we will change and will be dealing more with the sedimentary rocks.